Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Because we have Professor Booman from ETH Zurich visiting us, and he has kindly accepted to give this very interesting talk. And yeah, over to Professor Booman.
Okay, thank you, Pushmit. You will see whether it's interesting or not later on. Okay, so I would like to talk about a notion which I think is too often used and too poorly understood, and it's basically the question, what is information? In particular, context-sensitive information. What I really want to talk about is sort of this slightly different theme, structural learning and the generalization capacity of algorithms. What I mean by that is you have an algorithm, and the algorithm can extract from very large data some patterns, and you want to know whether that's for real or not. So we are now in the zettabyte age, and we want to make sense out of these data and build models automatically which, relative to what we are interested in, tell us how informative these data are. So let me give up front my scientific beliefs, and I have two statements which I think are at least interesting and debatable and hopefully controversial. And the first one is, mathematics as a language to describe reality has been invented for prediction. So sometimes I'm saying all mathematics is for prediction, but then you get too many people annoyed. So I believe when you bring mathematics in contact with reality, reality is always much more complex than your language. And that means it will introduce arbitrariness, randomness, and so on. And this has an impact on this language. And at the same time, for your particular phenomenon, you might use a language which is too precise relative to what you can measure. So there's an interaction between the two different areas. And the second one is model validation is more important than model design when algorithms generate models. So we enter the era where computers can invent models, and we no longer have the hardware requirement that a model has to fit at least in the brain of one person on this earth. This is a certain bias which has accompanied human mankind over the last 5,000 years or so, where we did systematic science. And this constraint might no longer be true. However, what we always want to make sure is that our models work in the future, and that means they have to be validated. How can we do that? So let me briefly give you, for one of the applications, we are pursuing the value chain of information technology. You start out with data, tissue microarrays or some metabolomics data. You convert them into information, presumably by looking at what doctors are doing. And then you extract knowledge from these data for the value of a patient. And the patient has a value when his survival in this particular context is increased. So the question I'm really interested in is the following. From this terabyte of data or hundreds of gigabytes of data, which bits tell me, which couple of hundred bits, maybe a kilobit or so, tells me about the survival of a patient as a function of the month? Because if we would know that a patient belongs to the prognostically good case, we could treat him in a completely different way compared to the prognostically not so good cases. So that's what I call context-sensitive information. I don't care about the majority of the bits here. I care about those bits which actually tell me about these two curves here something. How can we find out, and what kind of methods can we use? So to make it even more drastic here, you see this is a biopsy, I think from some skin cancer. You zoom in, you see something is not normal here. and I hit the wrong button. You go further down, and then you want to know where is that information. So what is the survival risk? Where is the information in that data set relative to these Kaplan-Meier curves? So I believe that there is a relation between machine learning and information theory, and in particular, information theory could serve as a model theory to address these types of questions. The only problem is information theory has primarily been devised for communication, and here we want to use it for decision making in a goal-directed way. So there are certain components which have not been addressed or not been used by information theory so far. There is a notion of an approximation capacity which measures the context-sensitive information in cost function and algorithms, and I would like to show you how you can actually measure these context-sensitive information and then rank your models according to their informativeness relative to your task. And then I give you examples. I hope I get through the examples. In particular, we worked on approximate sorting. And the other application is we were interested in validating spectral clustering. So these are the two types of applications where we have results. So what is learning? Well, given us some data, here I have the data, gene expression data, and we can convert them into graphs, correlation graphs, for example. And then you want to analyze these graphs, and in this context, you cut these graphs. So the hypothesis class is the class of all cuts. Or the second example is ranking. Here I have a bunch of objects. I have to get a new car. That's why this animation is with cars here. Here you have a preference matrix which says which object is preferred over which other object. And here you have a bunch of rankings. So what is common to these two problems is here is noise and here is noise. And that means I should not believe in a single solution on this side. But how big should be the set of solutions which is statistically indistinguishable under the variability here? This is the question which I would like to address. So learning is identifying a set of hypotheses in the hypothesis class. This set presumably should be small, but it should also be stable. So the learning game, as I perceive it, is the learner receives k instances and is tested on the k plus first instance, and at least we have to have 2 instances. If somebody gives you only 1 instance, he or she can always claim this instance comes from a Dirac measure, and no matter how often you measure, you always will get exactly the same data set, and therefore you want to have the global minimum according to your cost function for this data set. If you have 2 data sets and they differ, you know already there is some variability in there which should not influence your decision making. So the quality assessment is good generalization, as we know from information theory or from machine learning. But now the question is, what does that mean? Low risk, which risk function? Stable solution, how stable? Which generalizer to stabilize it? Information theoretic model validation for me is basically the attempt to put these types of questions on an absolute scale, on a quantitative scale, so that we can reason about different approaches. So the fundamental problem what we are faced here is how precisely should we approximate an empirical minimizer? If we approximate too much, we overfit. If we approximate too little, we underfit. So there is a trade-off. And the real problem there is my instances, when I do ranking, and the instances are given by these preferences, then the instance space is much larger than the solution space. The solution space is already large because it's the symmetric group for rankings. However, this is roughly n to the power of n, whereas this is 2 to the n squared. Most of the noise in my problem definition has no degrees of freedom to express themselves in the solution space. So that's the real problem. I want to know which noise is harmful, because I squeeze the signal together with the noise via the algorithm in my solution space. So this is something to keep in mind. Now, in principle, what a learning algorithm does, it quantizes the hypothesis class. So we have here a space of hypotheses. These hypotheses are, for example, the rankings, the permutations in sorting objects. These are the graph cuts for my graph cut application. And I would like to know how much this space is coarse-grained by the noise in my data. So maybe red is now the minimizer, orange is the approximation set, the set of solutions which I cannot distinguish. Is that appropriate? Or should I approximate more precisely? Or should I go for something in the middle? But now I get a second data set, x2, it's distributed according to the same distribution, and here is its approximation set. Not very good, overlap very small. If I use these solutions to predict on these data, I probably will do a poor job. Here I have a much nicer overlap. So the question is, if I partition this space too crudely in equivalence classes which I don't distinguish anymore, then I'm underfitting. I lose signal information. If I partition it too finely, then I get mismatches. How can I distinguish between these two different situations to find the optimal approximation precision for my optimization problem? And the answer is, I want to convert this into a problem which I at least have a rudimentary understanding, the problem of communication. In communication, you take the space of all bit strings, you randomly sample this space of bit strings using Shannon's random coding argument. You have your codebook vectors, and then you communicate the codebook vectors, and the receiver most likely will not receive the original codebook vector, but a noise perturbation of it. And as soon as you are in the right equivalence class, according to Hamming distance, you can reconstruct. So that's something we understand. Here we somehow have the same problem. And so what the strategy now is, I convert a hypothesis class in a set of equivalence classes, which I call approximation sets. Then I use them for communication, and I try to measure when the communication breaks down, because that's exactly when I'm unable to identify my approximation sets anymore due to the noise. And this gives me a quantitative argument how precisely I should approximate. So at the end of the day, with all this mathematical modeling, I tell you a number, and this number in the metric of your hypothesis class tells you what is the distance of statistically indistinguishable solutions. Then with that number, you go back and you do your favorite Bayesian analysis. You sample from that set with a probability distribution of that size. I would use the Gibbs distribution with a respective temperature and so on. You can do many different things, but you have determined in a quantitative way the precision with which you can actually resolve solutions in the hypothesis class. So the question is now, how can we achieve a coverage of the hypothesis class with these approximation sets? What is the conceptual problem behind here? The conceptual problem is you get one data set, or I told you get two data sets, and the training data set of these two data sets, the training data set has a minimizer here and an approximation set here. How can you devise a code in the sense of Shannon so that you roughly cover equally with equal spacing the whole hypothesis class? And that took me actually for a pretty long time, because Shannon randomly chose his codebook vectors from a probability distribution, but you don't want to randomly generate your data for your optimization problem. However, Shannon could have also done the following thing. He could have actually guessed one random bit string, and then he could have used this bit string and randomly permuted the bits. And now it becomes much closer to the scheme which we have in optimization. I have one optimization problem, but I can represent my data relative to the solution space using transformations. And that's exactly what I'm doing here. I introduce a transformation which shifts this minimizer down to here. I am not supposed to change my measurements, because if I fiddle around with the measurements, sure, I can't approximate as well anymore as before, because I might have destroyed signal. However, the transformation addresses only the representation of the hypothesis relative to the measurements. And this is under my control. And I then generate a covering of my hypothesis class using these transformations, in particular exponentially many transformations. And this gives me a criterion how to use such a cover. And in the following, I just tell you how to use, for the two different problems, ranking and graph cut, how I use this communication scenario to get a precise decision criterion for the approximation quality. Okay, so approximate sorting, I introduced that already briefly. I have these objects, I have a preference matrix, and I have here these rankings. The sorting cost function, which my PhD student Ludwig Busse was using, is a very primitive one. Whenever I is preferenced over j, but the rank pi is larger than pj, then you have sort of a mismatch between the preferences xij and the ranking, order, and then you count 1 in that cost function. So a very natural way of ranking. And how can you now convert this cost function into a code? So let's start now with the sorting problem. I have this preference matrix here. I have a bunch of cars here. If I have not made a mistake, then this is the rank order. So if you look, the second car has 1, 1 in that column. That means it's only preferred by one other car over it. So it gets this, the first position and so on. What you now can do is you can actually permute the ordering of these cars. And that would give you, if I just use the reverse order, it gives you a second preference matrix and a second rank order here. So the solution is different. The content of my measurements is the same. I have just changed the representation of my measurements relative to my hypothesis class, which are orderings. Now I do this 2 to the n row times, and row basically represents the rate for my problem. Now I get a second measurement. This is my second data set. We again ask people what the preference for these cars is, and you have one change here. So this is a change here. If you now look at the total order, then you get a slightly different total order based on this preference matrix. But now I ask you, which ordering did I choose for my test problem? Was it this ordering or was it this ordering? So what you do is you just look at the ordering here and the ordering here and here. And you see I used this ordering here. And I can do that based on looking at approximate rankings given for this data set. So in some sense, I ask now the question, when are transformations in my hypothesis class identifiable under the noise influence for my process? So how do we communicate? Very simple. First, we have to set up the protocol. I have a sender, a problem generator, and a receiver. And the problem generator distributes the data set x1 to the sender and the receiver. And the sender then calculates the solution, guesses these random transformations here. I use random transformation. You can also have a structured approach to it. And sends these transformations to the receiver. And the receiver can build up this huge table of approximation sets for these exponentially many transformations. I'm not asking the question how computationally feasible that is, because first of all, I want to know what to do in this context. The computational issues come later on. For communication, we have now the following scenario, which makes very clear what the problem is. The sender selects one transformation tau s and sends it to the problem generator. The problem generator now generates a second data set x2 and applies this transformation to x2. Now the receiver receives x tilde, which is tau s applied to x2. So the receiver has now the dilemma of seeing new fluctuations and a random transformation. And it has to guess the transformation despite the fluctuations. So if, roughly speaking, if the distance between two transformations, if the induced distance by a transformation in the hypothesis class is too short relative to the fluctuations, the receiver has no chance to estimate the correct transformation. If the transformation space is my approximation set sufficiently far away, then the fluctuations will have no influence on this decision process. So there's a clear-cut criterion in between. Okay, then the receiver calculates the approximation set with the minimizers, guesses tau hat, and now the game is clear. Whenever tau hat is not equals to tau s, I made a mistake. And so Shannon told us what to do in this context: calculate the capacity of this channel. It tells you exactly when the whole scheme breaks down. But the advantage is I have now sort of weaved into this whole process my cost function. So the a good cost function will sort of suppress the noise and emphasize the signal, and a bad cost function will amplify the noise and doesn't pay attention to the signal. So I now have this communication scenario to rank my cost functions. So the machine learning part is very simple in this context. First of all, I have to tell you how I actually make the estimate tau hat. Tau hat is the argmax of the approximation set on the first data set with a transformation tau intersecting the approximation set of the second data set where this unknown transformation tau s was applied to. And I take the maximal intersection between these two approximation sets. And I assume for the time being that I can actually do this intersection. Strictly speaking, you have to have a predictor function which actually tells you how to compare solutions on one data set with solutions on the other data set when you are not in the luxurious situation of IID data. But I'm suppressing this technical detail. So this is the quantity which we calculate, and this is my estimate. And the error event is very clearly whenever tau hat is not tau s, then I make an error. So in a nutshell, this is sort of the statistical learning theory which you have to use, and you should use it much more sophisticated here. The probability of an error conditioned on my tau s and my data set is the probability that the maximum overlap with the wrong transformation is larger than the overlap with the right transformation. This maximum gives me a union bound argument, and these non-negative random variables here give me an argument for Markov inequality, and what I'm ending up is this expression here. Now this expression might look a little bit opaque to you, but if you massage it, as I do it on the next slide, then you will see that a quantity which is very familiar to us comes out. The rate rho should be smaller than what I call I hat beta, and this is the quantity which was on the right hand side of my probabilistic estimate. And now I put together this tau, this capital tau, which is the space of all possible transformations, divided by C gamma, and C gamma was my approximation set. So this is somehow the way I can partition my sender hypothesis class, the hypothesis class for x1, with these approximation sets. If I take the logarithm, it's basically an entropy on the sender side. This is the respective entropy on the receiver side, and this is twice the joint entropy, because it's a coarse graining of the receiver hypothesis class with the intersection of the two approximation sets. So this is a mutual information, but it has, or I define it a mutual information, but it has weaved in a cost function into the way I calculate these entropies. And so my recipe is calculate this quantity here and maximize it with respect to the resolution beta, which is the size of my approximation sets, And with respect to all other parameters, you are interested in optimizing. So the model selection principle which I advocate is to use such a channel and to rank different cost functions according to their transmission capacity. I'm not really interested in communicating, but I use this communication metaphor to measure the brittleness of a cost function. And ultimately, I also want to measure the brittleness not only of a cost function, but of an algorithm, because I only needed this cost function to define an approximation set. So if you have a different way of defining an approximation set, you can apply it to an algorithm. And we know since Spielmann's work that you can use smoothed analysis of generating approximation sets. You don't have to have a cost function, although cost functions are helpful because they define a partial order on the whole hypothesis class, which is a lot of information. Okay, so approximate sorting, this is back to my problem. Now for approximate sorting, with that cost function, you can try to estimate these entropies. We are using mean field approximation for doing that. Because with these partial orders, I don't know exact methods for that. That's why I have a twiddle here. This is the term here. You evaluate it, you maximize it with respect to beta, and beta is the inverse temperature of my weighting, which defines the approximation set. Imagine that you have a Gibbs sampler which samples from the Gibbs distribution with that particular cost function, and then all the states which pop up frequently are the states which you admit to that. So approximate sorting with a Gibbs sampler can be done like this. And if you now look at the percentage of noise in the data set, here this is, I think, synthetic data. If the noise is increasing, this beta is decreasing. And if you then ask, how do you compare now your inference strategy with approximation sets compared to an empirical minimizer? And in this context, since we have two instances, we use the minimizer, which works good on both instances. That would be sort of fair if you have two data sets. Then you see that the error is significantly smaller for the approximation set strategy than for the joint minimizer. And it's very clear the joint minimizer overfits, even if you use two data sets. It will exploit the fluctuations which are jointly present in both data sets, and that's a small fraction too. So these approximation sets clearly should give you a better estimate. Here are some real-world data, and by the way, this is also one of the reasons why I came here. I desperately need data, large-scale data for rankings. Despite the fact that many people believe they have a problem in ranking, it's very hard to find large-scale data for rankings. Here we took the data from the German Chess League, year 2009 to 2011. This is the information capacity. It has a nice maximum for this beta value. If you use the joint optimizer, absolute error is 0.29, relative error 14%, and approximation set coding has roughly half of that error. So you do substantially better than what is already an improvement over the blunt empirical minimizer, because it's an empirical minimizer on two instances. So let me now come to algorithms. When you talk about algorithms, then they operate on the symmetric group. So these vertical bars here indicate rankings, and you have exponentially many of these rankings. And then the algorithm, a sorting algorithm, makes decisions. Merge sort, bubble sort, and so on. They make decisions. And so the hypothesis class of possible rankings is shrinking. And at the very end, your sorting algorithm comes up with a total order. That's sort of computer science 101. When you have noise in the data, blue is now the solutions which are still considered for both instances as solutions. You get deviations, and at the very end, your algorithm will come up with two different rankings because the fluctuations are different in your two different data sets. So you want to stop early your algorithm when this blue area of overlap is still sufficiently large. And that's exactly what Ludwig Busse did in his PhD thesis. So he realized that the sorting algorithms are guided by a monotonic dynamics which monotonically shrinks the still considered hypothesis class, and then stopping the sorting algorithm early will give you an approximation set. I'm not claiming that's the best possible, but this is the approximation set which characterizes this algorithm. Okay, if you then test these algorithms and you plot here the average deviation in ranks for a particular data set, and here the number of comparisons by the algorithm, then you see that bubble sort is not very good in terms of comparison. We know n squared and so on, whereas merge sort is very good, n log n. On the other hand, merge sort is not making a single redundant comparison, whereas bubble sort can do redundant comparisons. In the presence of noise, redundancy might be actually helpful. And that's exactly what you see. These algorithms are performing better than these algorithms with respect to their stability. Not with respect to runtime, but with respect to stability. So if you have, now this is an experimental setting, unfortunately we have only 16 items here, but 10,000 or 1,000 repetitions of these experiments. What you compare here are merge sort and bubble sort, and both algorithms are scaled in a very simplistic way according to their runtime. So bubbling length has been increased here, and merge sort has been performed with repetitions. And under these noisy sorting problem, here you plot the noise, and here you have the capacity of the algorithm, and here you have the bits extracted by the algorithm per comparison. What you see is that bubble sort, although inefficient in the noiseless case relative to merge sort, does a much better job above a critical noise level. So if you have such a noise level, then I would advocate that comparing algorithms only in terms of their runtime performance and their memory requirement is a partial view on benchmarking an algorithm. As another dimension which we should take into account is the sensitivity of that algorithm to input perturbations, and presumably also to perturbations to internal errors, programming errors, or maybe hardware failures and so on. And some algorithms are substantially better than others, and this is what you see in this context. So we validated now merge sort against bubble sort, and there is a threshold above which you have a preference for one algorithm to the others in terms of bits extracted per comparison. So as an information collecting device, bubble sort is better in this regime. Okay, let me now come to the other application where I now basically repeat the story, but for a different data structure and a different hypothesis class. And in essence, the outcome is comparable. So validating spectral clusterings. You have a graph representation. Vertices denote the objects. Edges represent dissimilarities or similarities, and I will give this example in terms of 3 cuts. So this is the adjacency matrix. This is my graph. This is the cut, and this is the solution here. So this reminds you of the situation which you have in sorting. How can I now code with cuts? Well, I have this graph, this adjacency matrix. I have this solution here, and I permute now the indices of my vertices. If I permute them within a cluster, nothing changes. If I permute them between the cluster, I get a different solution. So this is the new solution with the new cut, and I do this again exponentially many times. Now I get a new graph. Some edges have been added, others have been deleted. This is the new adjacency matrix, and you see the minus signs give you the deletions, the changes. This is the new solution, the new minimizer, and you can again guess, did I use this enumeration or this enumeration? And if you look at this pattern here, then you clearly see I used this enumeration. And again, here you have your sender, receiver, problem generator scenario. You distribute these graphs, you distribute the protocol, you build up the code book, and in communication, you send the transformation, now the transformation for transforming graphs. You find the approximate solution, you get tau hat, and you have again the mismatch between the transformation and this transformation here, the sent transformation. Now, if you apply this, for example, in real-world experiments, we used it primarily not in computer vision, but in bioinformatics. Then here you have gene expression data from some muscles. Over the 12 months, these 200-something genes have been monitored, how they change during the season of the years. And what the biologists told us, we should look at the correlation between the genes and then group these genes into groups according to their correlations. So this is the correlation matrix, and you have now a number of different approaches: normalized cut, correlation clustering, pairwise clustering, and we used even a new concept called dominant set clustering coming out of Pelilio's group. We used it for the same reason as for sorting. This is an algorithm which does not minimize a cost function, so it's just an algorithm. And so far, these types of approaches have been incomparable with the cost function-based approaches. So here are the cost functions for the three different algorithms. It doesn't really matter what they are in detail. This works very well in the vision community. This was a cost function which I championed for some time. With selling that cost function, I was less successful as Jitendra Malik. This is basically k-means in kernel space, so it has some good properties, but we didn't really know how to make that quantitative. Correlation clustering is very fashionable in document analysis these days, so people use that a lot in that application domain. And dominant set basically employs a replicator dynamics of evolutionary game theory to derive partitions. So these axes here could be interpreted as assignment likelihoods or something of a vertex to a node. So what we now do is we compare these different cost functions. Here is the information capacity again. Pairwise clustering has this maximum here for the stopping temperature. Normalized cut has this stopping temperature, but I like to draw your attention to the following effect. Here we have a mutual information per vertex of 0.8 and here of 1.4. So we now have quantitatively measured how many bits this cost function is able to extract from these correlation data of the muscle. If I use correlation clustering, then I get even a more a smaller value of bits, and it reflects in the number of clusters which I can extract. Here I think I have 7, and here I have 2 clusters. Here are all the different methods put together. K-means is around a little bit higher than normalized cut for these data. Here are the 7 different clusters which we get from pairwise clustering. That's now to be analyzed by biologists. You might actually ask, are these consistent, these clusterings for the different cost functions? So we plotted these 4 different categories. Yellow is object pair ij is clustered together by both algorithms, and then you have the other three other options. If you have a random clustering and compare it with the solution for pairwise clustering, this is how it looks like. If you compare correlation clustering with pairwise clustering, it looks much more regular, so the 2 clusterings sort of agree in their solutions. They are not random, but one method is much more informative than the others. Here is even more order. This is pairwise clustering versus normalized cut. So these are two good cost functions, but here for normalized cut I have 0.8 bits, and for pairwise clustering I have 1.2 bits, and this reflects in more stably extractable clusters, which means the pairwise clustering cost function on these data, and I should emphasize it's a data-specific statement, on these data it extracts more reliable structure. Here on a much larger data set from gene expression data, this is the analysis, and now the biologists are sort of debating whether 14 clusters or 9 clusters are correct. You also see that sometimes this curve is not so nice, smooth, monotonic, which might be related to substructures which can be resolved only at certain preferential scales of clusters. The last experiment here is something where we compared this dominant set algorithm and pairwise clustering, but for different metrics in the data space. So you compare this according to Euclidean distance or path-based distance or correlations, and you see that the distance might actually make a bigger difference than the methods to extract these structures. So blue is pairwise clustering, and red is dominant set algorithm clustering, but what really pays off is that you look for these connected structures, these paths in your data set. So the capacity is by far the highest for pairwise clustering with path-based distance metric. How can you explain this? Well, look at the spectrum for path-based distance compared to correlation-based distances. You see the spectrum for path-based distances decays much faster, which means this transformation compresses the signal in an effectively lower dimensional space, and there you can better extract these different clusters. So we know from our studies, which we did years ago on pairwise clustering and dimension reduction, that if you go from high dimension to low dimensions, often you suppress the noise effectively in these relational data. So let me come to an end. So basically, noise in the data quantizes your hypothesis class. And with that quantization, you generate new structures which you might use as symbols in a fictitious communication scenario, and then these symbols can be used for coding. When you code with these symbols, you can determine for the respective algorithms or cost functions something like an approximation capacity, which is the length of the resolution of your hypothesis class where communication breaks down. And that's exactly the optimal approximation for your cost optimization problem. And this quantization allows you then to count the number of distinguishable solutions in the hypothesis class, and effectively this gives you a structure or a context-sensitive measure of information. Context-sensitive with respect to an hypothesis class. You change the hypothesis class, you measure a different number of bits in your data set. So this is very clear a notion of information which I appealed to in the very beginning. I want to know in this medical data set which bits tell me something about survival, not about the staining process, not about the age of the patient, not about his diary, his eating habits and so on, about his survival. And so I have to specify this context, and this context is specified in terms of a hypothesis class. So at a more general scope, I like to advocate this notion of generalization, and in particular we have to investigate more in detail how it applies to algorithms, in particular algorithms which are not directly related to a contractive dynamics on the hypothesis class. And the other thing is the problem of overfitting is not only coming up in learning and computer vision and the traditional pattern recognition areas. They come up in the area of partial differential equations. For example, in systems biology, we had a project where we investigated the liver metabolism, and people there tell us that diabetes, to be understood, you have to basically monitor 1,000 to 1,500 ODEs and determine their activity, their behavior from data. The question is, if you want to have only 5 ODEs and they should explain as much as possible about your phenomenon, which 5 would you choose? Or even more interesting, if I give you 5 variables and you can choose whatever variables you like, which one would you use to describe this system of 1,000 ODEs? You can build up compound variables which sort of put together information which is relevant for describing your phenomenon. So model reduction in dynamical systems, I think, is a very promising direction where a lot of people really would like to know what is the information content to be extracted. And more sort of in the context of computer science, we have there 2 notions of complexity. One is statistical complexity, the one we use when we have a generalization bounds or in information theory with a capacity calculation. And the other one is the computational complexity. How does that relate to each other? With that study on clustering, we have, on sorting, we have seen that the runtime of the algorithm was basically a measure for the size of the approximation set. There very directly, the computational complexity was linked to the statistical complexity, and we had a stopping criterion which was based on statistical analysis, on decision theoretic arguments. So they are linked together, and this relates to the observation of many practitioners that when you have a hard optimization problem, it becomes particularly hard when you start overfitting and you don't notice it, because then you have to sort out the fluctuations. So linking these 2 notions together is beneficial in two ways. You don't pay too much for your computation, and actually you predict better in the future. And I think these are the main motivations why we should look into these questions from a computer science point of view. Okay, thank you very much for your attention.
Thanks, Joachim. We have time for questions. Okay, I'll ask one, which is, I mean, that work with the sorting algorithms was very interesting. I mean, is there sort of a way to actually reason about what are the right approximation sets and sort of get insights which could lead to better sorting algorithms that can deal with particular types of noise in the data?
Yes, the way we reason about these sorting algorithms is to set up these experiments. We get the data, we have these 2 data sets, we measure their sensitivity up to the point where we overfit. That's exactly determined by this mutual information. So these are just set theoretic considerations, and that gives us a stopping criterion. And so in principle, what I believe is you should measure the individual steps of an algorithm with respect to their brittleness under these uncontrolled perturbations. They might come from the input, and then they are frozen. That's what a physicist would call a quenched averaging. They might come up from the dynamics of your hardware. We talked about this. There is new hardware out there which actually allows you to invest a lot of energy, and then you get crisp bits, or to have energy-saving computation, and then sometimes the comparison in the language of sorting is wrong. So you get the wrong results. If you would have a way of designing an algorithm which is sort of a low-cost energy low-cost algorithm, such that it makes the mistakes where it doesn't matter for your problem, then you could actually get away with much less investment. If the hardware would support that, that's fine. There is a best paper award, I think, in one of the hardware conferences a year ago or so on such a hardware. But we have to learn how to design algorithms which actually support this hardware. And that means we have to have a theory which allows us to measure at individual statement level how sensitive that statement is in that dynamics. And so in some sense, we have to have a meta-criterion which validates the algorithm, step by step, routine by routine, and so on. And that's how I would proceed. Now, this is all Mickey Mouse level type of analysis compared to what the challenges really are. But up to that point, I didn't even know how to evaluate an algorithm. I had an EU project called SIMBAT, Similarity-Based Pattern Analysis, and with Pelilio. And we were fighting almost 4 years in that 3 years in that 4-year project, because he was on evolutionary game theory and I was betting on cost functions. And the reason was we didn't know how to compare. Here is a way to compare it. We have a bit number. He can question whether we calculated the bit number correctly or not, but this is a fair game. It's a mathematical statement, and period. And on these data, he is not looking as good as we do. There might be other data where he is doing better, but that's basically the theory which is behind it. What is still lacking is a lower bound, but I think I can get it from a generalization of Fanos inequality. So.
Okay. Any more questions? Okay, let's thank Joachim again.